Two important notes to make about the structures and bonding associated with amines. First one is I will refer you back to what really is the simplest amine, the one in which all of the R groups are hydrogens. That is ammonia. And indeed, I'm going to use ammonia as a starting template quite often during this particular module. Anyway, of course, we studied ammonia extensively in terms of its structure when we were back on Lewis structures. We said, well, the nitrogen has got 4 electron groups around it. 3 of those are bonding, 1 is a lone pair. So the ideal angle would be 109, but of course that lone pair pushes things away a little bit more than the bonding groups push each other away. So the angle in ammonia, 107 degrees. Same general idea when we actually move to the amines that have R groups in there, except that of course an R group is a little bit bigger than a hydrogen is. So what we see in methylamine, for example, hopefully you recognize this as methylamine, CH3NH2, is that the angles are asymmetrically distributed. Where you've got the methyl group involved, it's pushing the hydrogens away a little bit more, so 112 degrees, and those poor little hydrogens are squished together at 106 degrees. Now, it's an important angle that we rarely discuss up till now, but it's going to help us introduce a rather significant concept. And that is, I'm not going to really call it the dihedral angle because it's not, but it's the angle between this CH3 and the bisector of these 2 hydrogen atoms. Okay, so I'm bisecting those, and what's the angle between the methyl group then and kind of in between the hydrogen atoms? And in this case, for methylamine, it's 125 degrees. Now, it's important that you appreciate that this angle in a tetrahedron is less than 125 because we got the whole thing bent by that lone pair. If that lone pair wasn't there and the nitrogen was trigonal planar, this angle would be 180 degrees. Now, consider then the structure of aniline. Okay, that's the phenyl group. I'm trying to draw it flat on, so that's coming out at you, going to the nitrogen, and then 1 hydrogen coming out at us, 1 hydrogen going away from us. Okay, no real reason to expect anything different in terms of the structure of aniline, except when we look at that funny bisecting angle there, what we find is that it's 143 degrees. In other words, it's not what you would expect when you have just a regular trigonal pyramid. It's much closer, significantly closer, to being a trigonal planar nitrogen. Now, why is that? Well, the reason is the standard idea. Anytime you see an aromatic ring there, you think to yourself, well, can we extend the delocalization to include atoms that are put on it? And the answer is, of course, we can. This carbon here in the aromatic ring has a p orbital that's sticking up and down. Okay, and of course, all the other carbons have p orbitals sticking up and down, and those overlap to give you that pi cloud. Well, this nitrogen lone pair is in a p orbital that's effectively sticking up and down. Nitrogen orbitals about the same size as carbon orbitals, so we can get a nice overlap between this p orbital on the carbon and the p orbital on the nitrogen, which means that these electrons here can be incorporated into the delocalized electrons going around the ring. Now, the way I show this is we show some little resonance structures. So we take aniline, take the lone pair of electrons and bring it in to the benzene's pi cloud by making an extra pi bond here. So we're using these p electrons, now turning them into pi electrons. Then, of course, we have to have the appropriate shift of other electrons around the ring. So the first resonance structure we get that's bringing these electrons into that pi cloud is taking the lone pair, putting them into a pi bond here. And then, of course, now we've made the nitrogen positive because we're taking away electrons it had all to itself and sharing them. And because this is a neutral species, we must also have a negative. Well, we see that for that carbon there. Right, when the nitrogen shared its lone pair to make an extra bond here, this carbon says, oh, now I've got 5 bonds, I don't want these pi electrons anymore, so they got shifted to this carbon, making it negative. And then, of course, we can continue to share that negative charge around the ring, putting those electrons from being p electrons on the carbon to pi electrons here, at which point this carbon says, well, I don't need these pi electrons, so they get shifted onto that 4 carbon. So our second resonance structure is like that one. Continuing on round the ring, these p electrons become pi electrons, so these pi electrons become p electrons. And we get this resonance structure. And then, of course, if I wanted to continue, these p electrons would become pi electrons, at which point these pi electrons would become p electrons, and we're back to this structure. Now, this is a structure in which there's no separation of charge. These 3 resonance structures, we're taking a plus and a minus, so they're not as significant resonance structures as this, but they all contribute. Now, the effect of that is twofold. The first is that now the nitrogen in these resonance structures is, of course, trigonal planar. It's got 2 bonds to the hydrogen and a double bond here. So it's got 3 groups of electrons around it, and 3 groups of electrons are trigonal planar. So that's why aniline is between 125 for the tetrahedral, this structure, and the 180 expected for those structures, because you have contributions from these resonance groups. The other huge thing, and this harks back to our aromatic discussion, is now we are putting extra electron density into the benzene ring from this lone pair on the nitrogen. In those extra electron density into the benzene ring, that means the benzene ring is even more of a nucleophile. It's even more attractive to electrophiles, which means that aniline is one of the most reactive aromatics. If we go back, phenol, very reactive because the oxygen has this lone pair that it can put into the ring. Aniline even more reactive because, of course, oxygen is more electronegative than nitrogen. Nitrogen is therefore more willing to share its electrons than oxygen, so aniline even more reactive than phenol.